Yeah, perfect. So yes, we talked about the gain error, but we left at V offset, right? So we left at V offset error. So what we basically do is we try to imagine a line, or we try to um, create a line which is straight in function. Obviously, if we try to make a slope of this line, it will not be a straight line, but somehow we try to make it straight, and we try to make it a best fit for this staircase, and then check the difference between the main staircase and the original line we tried to fit into this staircase. And that's how we shift it to delta by 2. And because this is the delta, right? So this line, this slope will start from delta by 2 at this point. So then we subtract it and clear out the V offset error. So yeah, that point I left in the last video. So we'll start with this video. And until now, we saw the non-idealities while quantization, and none of those will occur in isolation. I mean, one time a gain error, next time the V offset error, they will not occur in isolation or a single error. Um, any practical ADC will have all of these non-idealities together. Like basically, we discussed about V offset error, gain error, non-uniform step size, etc. So all of them will occur together in any practical ADC. So then DNL and INL are two ways of conveying the same information, right? So now we need to look at the spectral properties of the quantized signal. So we saw, until now we have an idea of what a quantization is. So then we say that we have X in to the quantizer. So this X in is continuous or discrete? Can anyone tell me? Anyways, we had already done sampling, so we have considered over here. I mean, we have already covered sampling, so this is the discrete time signal. This is the sampled signal, which is a sequence of n. So we have xn of n. If it would have been a continuous signal, it would have been xn of t, because it's the function of time. So, but now it's a function of n sequence. So this is a discrete signal, which is the input to the quantizer. So let's imagine the quantization process in a box. So this is how we define a system of a quantization. Like every system, this is how we define. So let's say we have x in a sequence at the input of a quantizer, which is continuous in amplitude but discrete in time. And then we are getting a signal xq, which is quantized in amplitude. So this is discrete in time as well as discrete in amplitude. So we know that the input output characteristics of this quantizer is extremely nonlinear, because every step we have some non-linearity. I mean, the behavior is the transfer function is extremely non-linear, and mathematically it's going to be a very difficult task to deal with such kind of a system when we design the system mathematically. So if a quantizer is not overloaded, so we saw what is overloading of a quantizer. So basically we are talking about the uh, range of VREF. So in the range of VREF, basically there the quantizer is not overloaded, and that's the range of interest. So then if the quantizer is basically non-overloaded, then the difference between the input and the output will be basically xqn minus x in n. So that's what I've written over here. So it's the difference between two sequences, and that's called basically a quantization error, because that's coming from the quantization. So we have an ideal quantizer over here, and we have the step size uniform. And when we consider or assume this to be true, then only, then only we say that xq minus xn is our quantization error. So clearly the quantization error, uh, if these conditions are satisfied, is bounded by a step size. So this is the error which is bounded by minus delta by 2 to delta by 2, where delta is basically our step size. So given the input, I mean, if we know about, we have the knowledge about the input, which is x of n, we can like predict the quantization noise or not. I mean, that's the question. Like, what is the correlation between the quantization noise and the characteristics of xn? So basically, for a given input and given characteristic of the quantizer, clearly xq and xn is a known quantity. We know xn as well as we know xq. So it's a known quantity, which means the quantization error is determined, or basically it's deterministic. We can determine it. It's a known quantity. So it's a deterministic error, and it's not a random error. So we can talk or see the spectral characteristics of this error because it's a deterministic error. So basically, if we want to talk about the quantization error, and we can do one thing, that we have xn, right? And we have xq. And we said that xq minus xn is basically our quantization error. So let's do one thing. Xq is obtained by quantizing xn. So we have xq over here, and we'll take xn, and we'll have a subtractor over here. So which will take the difference between xq and xn. So basically it will give the quantization error. And how the spectrum of the error will look like? So the error will go on increasing, and as the transition occurs, it will again start with the next step. Again, it will go on increasing. Again, that step will change. So we again have a transition. So it is like a sawtooth waveform where it is bounded definitely by delta by 2 and minus delta by 2, where delta is a step size. So if xn, let's say it's a sinusoidal sequence. So it is represented, as any sinusoidal sequence is represented by a cos a of n. So it's a sinusoidal input to the quantizer. Then what would be the spectrum of the output of the quantizer? Can we comment on it? So basically I'm saying that if xq is the output, which is a sequence again, so it is coming from a quantization of a quantization. So what we are saying is basically we have a xq, which is a quantized sequence, and which is coming from quantizing a sinusoidal sequence, which is x of n. So then we know that from this error, so basically over here from this equation, we know that xq is basically xn plus error, because error was xq minus xn, right? So xq is basically nothing but xn plus error. So we can look at this and in another way. So basically, the quantization error can be found by simply taking the input and passing it through a box whose transfer curve looks like a spectrum error. So like this. So we, like, based on this, we can comment that the quantization error, so basically it can be found by simply taking an input, which is xn. So we can take an input, and which will we will pass it through a box whose transition curves looks like this. So we have xn, and we have this spectrum of the error. So we have xn plus error. So it will basically give us the quantized sequence. So that's the one way of looking at it, because we are defining the characteristics of the spectrum of error. So if we take a sinusoid and pass it through a block, which is, yeah, obviously non-linear. So, I mean, yeah, this block. So this is, yeah, we know that this is not linear. This is non-linear. It has so much of spikes and transitions. So if we take a sinusoid and pass it through a block of an error, which is non-linear, we expect a lot of harmonics in the output. Why? So we have seen this earlier also. So when we like look at the output spectrum, if there are discontinuities between the signal and we plot it, so then if due to the discontinuities, we'll get the harmonics for sure, and we'll see a lot of harmonics because we have a lot of discontinuities over here. And this is one thing to be noticed, and hence the quantized sinusoid will have many harmonics basically of the input or the fundamental input. And due to the lot of discontinuity in the transfer curve of the block, finding the harmonic content is very hard. I mean, yeah, we know there are many harmonics will exist, but finding how much or the content or exactly the magnitude of harmonics is very hard because we have a lot of discontinuity. So uh, basically, it seems like this is a very challenging task when it comes to do when we talk about doing it mathematically. When we try to analyze the spectrum, then also due to the lot of discontinuities, uh, it's getting very hard. I mean, it's very hard to do this. So then. The book comes with a solution, so it's an engineering book. So anyway, like theoretically it's not viable or justifiable, but if it is working in practical, then and ultimately we are engineers, so we are going to find the solution because solution is our task. So the book says that at this point we need to make approximations based on intuitions. So there are some approximations which we are making, which theoretically may sound questionable, but even though like the assumptions are mathematically questionable, only justification we have as of now is it works in practicality. So in practice, it works. So then the assumptions or the approximations are basically we treat the quantization error as a white noise. So this is the first thing. So we treat this error as a noise. So we'll see how it helps us. So the noise is independent of the signal, which is input. So it is independent of input. This is the second approximation we take. Then the error is bounded and also uniformly distributed between minus delta by 2 to delta by 2. So we say that this is uniformly distributed and bounded. So the quantization noise is independent, or let's say it's the white noise, and which is broadbanded. So we have talked about the broadbanded noise in the first video itself. So now when we have done all these approximations, when the noise is uniform between minus delta by 2 to delta by 2, this means that the mean squared value of this quantized noise process is basically delta square by 12. So where did it came from? So it's bounded, and we have considered it as a white noise. So it's uniform between these two boundaries. So then the mean squared value, or basically the variance of the noise, comes out to be delta square by 12. And for a n-bit quantizer, so we know the quantization, we studied it in the last two videos. So for an n-bit quantizer, we have 2 to the power n steps. So basically this is the range of quantizer, right? So which means that the maximum amplitude of the sinusoid which fits the range of quantizer is 2 to the power n minus 1 times the steps. So basically we are familiar with this. So if I show you the quantizer, so where is the ideal quantizer over here? Yeah. So let's say we have 2 to the power 3. So this is a 3-bit quantizer. So if this is a 3-bit quantizer and this is 1 delta, so we have delta times 2 to the power 3 minus 1. So 2 to the power 2. So we have step size into 4 as our range of the voltage. So that's what we are talking about. So the maximum power we can pump in without saturating the quantizer will be basically called as signal power. So it will be the square of 2 to the power n minus 1 times delta square by 2. And the quantization noise power we saw here, it will be delta square by 12. So if we take the ratio, then it is called the signal to quantized noise ratio, and this SQNR comes out to be the division of these two. So basically it comes out to be 2 to the power n minus 1 square times 6. So this is the SQNR, and when we talk, we always talk about noise in dBs. So when we convert it to dB, so we convert this into dB. So we have 20 log the magnitude of this. We have 20 log magnitude of this, but we are taking a ratio. Therefore, the it is 10 log of the SQNR. because we are taking the ratio itself. So it's not 20 log SQNR, it's 10 log SQNR, which comes out to be 6.02 times n plus 1.76 dB. So every increase in the bit number, so we have the bit number here, every increase in the bit number will increase the SQNR by 6 dBs. So we'll see how. So this sentence makes sense, right? So reduction is so basically the reduction in SQNR by 6 dB. So by a factor of 4. If it is reduced by a factor of 2, then it's reduced by 3 dB. If it is reduced by a factor of 4, then it's reduced by 6 dB, which is equivalent to the noise power going down by a factor of 4. So that's what it is, right? So SQNR is basically signal power by noise power. So we say that the reduction in SQNR by 6 dB, because it's 6 dB over here, is equivalent to noise power going down by a factor of 4 when normalized with respect to the signal power. So if we have increased the resolution by 1 bit, so this increase by 1 bit, as we said earlier, every increase in the bit number will increase the SQNR by 6 dBs. So if we increase the resolution by 1 bit, the step size, basically LSB, has gone down by a factor of 2. And the power of the error, which is basically the quantized noise, goes down by a factor of 4. So this thing or these sentences should make sense. So let's say we have a quantized sinusoid. So we have a sinusoid signal, which is basically a x of n because it's a sequence. So we have a sinusoid sequence. And let's say we quantize it and we plot the FFT after quantization of this quantized sequence, then what things can we expect in the FFT? I mean, we have seen the FFTs. We have also talked about the FFT leakage. So if you guys remember, we have this relation. So we have talked about it. So F in by Fs should be, this condition should be satisfied if we want no FFT leakage. So let's say this condition is taken care of and there is no leakage and the input lies on the bin itself. So then what would we expect in the FFT of the quantized sequence? So how would we basically, if we plot the FFT, so basically if we take the n sequence and repeat it periodically, and if we plot coefficients of the discrete Fourier series, so then we have the magnitude in dBs. So let's say the signal input lies in the mth bin. So basically this is n by 2. Then the noise, so we will see the signal over here, but we also have a noise with the signal, right? So we have also have a quantization noise here, and it is a white noise. So it will be spreaded all over broadbanded bins, and it will look like this. So this is a noise. This is a quantized noise. So how would we come? So this is what we expect the FFT or the coefficients of discrete Fourier series to look like. And we plot it, and when we assume that this is taken care of, this condition is taken care of. So how would we compute the SQNR given that this plot and nothing else? So when we look at this plot, can we compute the SQNR? So you might think, yeah, it's very easy. We have this magnitude, we have this magnitude, we'll take the ratio of this magnitude. So that is the most common mistake everyone do. So basically the question is, how would we compute the number of bits of the quantizer, or can we comment something on the SQNR, because both are related, right? SQNR is related by number of bits with this formula. So yeah, so the comment is the signal power is simply the power which is presented in the mth bin, but the noise power is the power of the noise in all other bins, because it's a white noise and it's spreaded throughout the bins. So the ratio will give us the SQNR. So we will take the power of this input, but the ratio of the noise power will be power of all the bins, not just the single bin. All the bins power is clubbed together, and that gives us the power of noise. And then we take the ratio of power of signal to the power of noise. So then we know that SQNR is this sequence, I mean this equation, and then we can find n from here. So we can compute the number of bits of the quantizer looking at this graph. But yeah, the common mistake is this is not the SQNR. So I mean this, so this magnitude divided by this magnitude, this is not the SQNR. And if we, I mean, we can talk about this. So if we increase the n, so now it was from here to here. So this was our n width or the record length, right? So instead of this, if we increase the record length to this point, so then our n by 2 will lie over here, not here. So if n by 2 is lying over here, so this much of noise will get spreaded more. So basically, if we double the record length, then basically the um, noise will be halved over y-axis, and it will be spread throughout the end. So if we increase the record length, then the noise will be spread over more wider range, but the total power of noise is delta square by 12. It is not changing. So when this will increase, so this distance will decrease because it will spread over a wide range. So this distance will basically increase. So yeah, definitely this distance is not giving us the SQNR. So we have to take the power of the signal, power of all the bins for noise. So in practice, the quantizer staircase is not as nice as we wanted it to be due to the several non-idealities. So when we actually take a non-ideal quantizer or a practical quantizer and plot the FFT of the quantized sequence, so along with the fundamental peak, we will also see some harmonics, and they might alias back and will not look like they will look like a low frequency tones. So we have seen the how the harmonics alias back or folds back to the bins, and they look like they are low frequency tones, but they are the harmonics. So we actually compute the SQNR in this case, and we found out that the actual SQNR is smaller than what we expected. So this is for ideal, right? So when we take a practical one, then the SQNR of the practical ADC is always lesser than the ideal or the mathematical driven SQNR. So then, for example, we have got a 10-bit quantizer, which means in principle, we will expect SQNR about this value. But in actuality, we only get smaller SQNR, which is somewhat related to 45 or 50 dBs. I mean, these are just the layman terms. So in this case, what happens in this case? So in practical case, there is a need for more scientific method of qualifying the performance of the ADC. And one such metric, we need metric to qualify it scientifically, right? So one such method or a metric is called effective number of bits, ENOB. And ENOB is given by the actual SQNR minus 1.76. So SQNR had some factor of 1.76 over here, right? So we have actual SQNR minus 1.76 divided by 6.02. So this will give us the ENOB or effective number of bits. So then we can see the plot on the screen where we have a sinusoidal input sequence and we have a quantized output sequence, and this is the quantization noise or the quantization error. And we can see where there is a serious transition in the input sequence, then we can see the noise to be affected in this manner. And so basically this is for, let's say, yeah, this is for 2 to the power 3. This is 3-bit quantizer, and we also have 4-bit quantizer. So step size will be 2 by 2 to the power 4. So then we have the sinusoidal input, we have the quantized output, and again we have the noise. So we can see here that the noise is spread evenly over here. But then if we increase the record length, then the noise is even spread over a wider range, but the power of the magnitude, like power of the noise, will be delta square by 12. So then the magnitude will be decreased. So first, let's say if this is, I don't know, 1/4 of 0.25, and this is half of 0.25. Yeah. So yeah, we have doubled. So basically it will be half. Yeah, perfect. So we can also look at the FFT of the quantized output. And let's say we have taken at the bin 129. So this is our signal lying on the bin 129. And we can see the noise is looking like this. So yeah, I mean, yes, even this noise is not um, what we say, like this is the practical ADC, right? So even though we have made approximation that it is a white noise and it is broadbanded and it is evenly spreaded, but in practically we can see that they are just approximation, but the noise is not white noise though. But yes, in the end, the ADC is something we need to get working. So that's the task of engineers. So yes, so this is the FFT which will look like of the quantized output. So yeah, this is all from my side for this video. Thank you so much. If you have any doubts, do let me know.
Thank you, Ishi. No doubts, but do you have code for all this waveform? Like, did you do in Python or
Yeah, in
uh,
Python.
MATLAB?
In Python, yeah. I'll share you the code for this.
Yeah, yeah. Okay, Rishi. Yeah, yeah.
Okay,
I understood. And yeah, no doubts from my end.
perfect. What about Hania? Peter?